Good evening, GCC. I hope you're doing well today and staying safe. Whereas we continue looking into Chapter 6, yesterday's lesson, 6.6, that was a key lesson. That kind of put everything together. The last three sections are mostly applications. 6.7, we're going to look at financial models. Have your calculators ready. We're definitely going to need those today. So in the financial models, we often deal with things like exponential growth. If you make an investment, you want your money to grow. And exponential decay, where if you're paying off a loan or a credit card, you want that the amount you owe to go down very quickly. So we're going to look at a couple of things. We're going to see a lot of formulas today too. Now with the formulas, you don't need to memorize the formulas. The formulas will be given to you. You just need to be able to read a problem, look at it, and know which formula do you need to use. The first formula is something called simple interest. And here's the formula. I equals PRT. And it's not by accident that I'm using a capital I, a capital P, a lowercase r, and a lowercase t. The capital I here, this is the interest. The capital P is what we call the principal, or the initial amount. The R is the rate, and the T is time, usually in years. So, and watch out for this, by the way. If the time was going to be every 3 months, then that would be 3 months would be 3 out of 12 months a year. That would be 1/4 of a year. You have to put it in years. The rate, if I've got 6%, I have to put that in as a decimal, so 0.06. The principal is usually the dollar amount. I'm investing $10,000 or something, and then the I is the interest that you're going to have at the end of this amount of years. All right, let's look at a very simple, very basic. This is our kind of our first level model here. Let's take a look at a very simple, very basic question. Suppose I'm going to invest $1,700 at 6.5% simple interest for 1 year. So suppose I out of the middle of the blue, out of the middle of nowhere, I get a check for $1,700, and I decide, you know what, I'm going to put it aside. I'm doing pretty good now. I'm going to put it aside for a year. How much would I have in a year? Well, this is a simple interest problem. So the formula, interest equals principal times rate times time. The interest that I'm going to earn on this will be the principal, that's the $1,700, times the rate, I have to put it as a decimal, 0.065 for 1 year. This will show me how much interest I'm going to get on my money. Here comes the calculator. We're going to be using these a lot today. 1,700 times 0.065 times 1 year. Okay, so that equals 110.5. Well, what does that mean? Well, this is the interest in dollars. So $110.50. That's how much extra money you'll have back in a year. And you're not doing anything. You just put this money in the bank. That's how much interest you'll have a year later. And of course, you'll still have the $1,700. All right, so that's simple interest. Very basic. There are, if we take a closer look at this formula, 1, 2, 3, 4 different variables here. And I should be able to give you any 3 of them, and you find the other one. For example, I could give you how much was invested and what the rate was and how much the interest is. And you have to work backwards to find out how long that investment was going on. Or maybe I know how much I'm going to invest, and I know for how long I want to invest, and I know how much I want to get back. What rate do I need? So with these, I could give you any 3 of them, and you need to be able to find the 4th one. Pretty straightforward here. Nothing too crazy with the exponentials or anything yet. That is definitely coming, though. We'll see that. In fact, here it comes. In the next formula, we're going to deal with something called compound interest. The compound interest formula, a little bit more complicated. A equals P times 1 plus R over N to the power of N times T. Oh boy, okay, let's break this down. So what are all my variables here? A is the amount that the investment's going to be worth after time. The P is the principal, the initial amount that you're plugging in. R is still the interest rate. And again, we have to put that in as a decimal. T is the time in years. You'll notice, you'll see a lot of these variables again and again in different formulas, and they always mean the same thing. The new one here is the N. What is the N? The N represents the number of compoundings per year. In other words, how many times are we calculating the interest that in 1 year? All right, so let's kind of put it all together here using this formula. Let's look at a sample problem. Suppose we're going to invest, let's take that $1,700 again, and this time we're going to invest it at a lower interest rate, so less than my previous 6.5%. Let's say this is going to be 5.9%, but instead of only compounding it once a year, like simple interest, this is going to be compounded weekly. The interest is going to be accrued every week. Every week they're going to put interest on this. So at the end of the first week, you're going to get a little bit of interest. At the end of the second week, you're going to get a little bit of interest again. But you will also earn an extra interest on the interest from the previous week. I know, it's very confusing. Every week, you get interest on how much is in there, and you get interest on the previous interest, and interest on the previous interest, and so on, compounding. This is the power of compounding. All right, so let's take a look at the formula here. We have amount equals principal times 1 plus R over N to the power of N times T. And ladies and gentlemen, one point of emphasis here, whenever you're working with these formulas, and really at all in any math class, whenever you're working with formulas, always write the formula down and then substitute the numbers in. All right, so here we go. We're going to put the numbers in. So the amount that this is going to be worth. Oh, how long? How long? Let's do. I didn't give a time frame here, did I? So we're going to invest $1,700 at 5.9 cents compounded weekly for 1 year. There we go. So the principal is $1,700. 1 plus my rate, 0.059 over the number of compoundings per year. Well, if I'm doing it weekly, that's going to be 52 times a year to the power of 52 times 1 year. So my rate, the 5.9%, is broken up 52 times. So it's a very, very small rate that I'm going to get. But I'm going to get that rate every week, not only on this, but on the previous week's interest, and so on. All right, so calculator time. Let's see how much this is going to be worth. So 1,700, open parentheses, 1 plus 0.059 divided by 52, close parentheses, to the power of, now be careful, if your calculator doesn't jump up there in the exponent like this, if it just gives you the chevron button, you probably want to make sure that we put the top, the exponent, in parentheses. 52 times 1, open parentheses, 52 times 1, close parentheses. And of course, the next example is not going to be 1 year. Hit enter, and it looks like the total amount this is going to be worth is $1,803. And with money, we always want to round to the nearest penny. This is 0.257, so I'm going to say 0.26. So that's how much this investment is going to be worth. Now I could work backwards and say, well, how much interest did you just earn? Well, this is the total investment. This is the total amount that it's worth. The previous formula was only the interest. So if I take out the original $1,700, it looks like I'm getting back an extra $103.26. All right, let's look at another one, and then we'll talk about this formula a little bit more. In this next one, let's say you have a rich uncle that passes away, and in the will you get, so you inherit $8,200. Well, you decide that you're going to throw a party and have a little bit of fun and buy some things and pay off some credit cards with about $1,200 of this. So you want to invest the other $7,000. You're going to put, take the $1,200 off top, have a party, pay off some bills, buy something nice, all that kind of fun stuff. Uncle would have wanted that. But then you're going to take the other $7,000 and you're going to invest it. So you go down to your bank, and your bank tells you that they will pay 5.75% interest compounded monthly. And you decide you're going to put this money in the bank and let it earn interest while you're at college and taking classes. So you're going to leave it in the bank for 4 years. And then let's see how much is left after 4 years. And then when you get out of college, you're going to use this money to get a new car or down payment on a house or something. But while you're working in college right now, you just want to put that money aside. You're going to put it in the bank, and you're going to walk away for 4 years. When you come back in 4 years, how much is that $7,000 going to be worth? Well, we've got a compounding problem here. Amount is principal times 1 plus the rate over the number of compoundings per year to the power of the number of compoundings per year times time. I'm saying it in English, and I'm writing it in math. Always write the formulas down. Substituting in, the amount is going to be that $7,000 principal investment, 1 plus the rate is going to be as a decimal 0.0575. The number of compoundings monthly would be 12 months in a year to the power of 12 times 4 years. So now it's all about putting it in the calculator. Be careful on how we put it in the calculator. All right, here we go. So let's see, 7,000, open parentheses, 1 plus 0.0575 divided by 12, close parentheses, to the power of, and again, be careful, make sure this whole thing's in the exponent. I'm going to open parentheses, 12 times 4, close parentheses, equals, and my investment after 4 years is worth $8,805, round to the nearest penny, and 36 cents. How much interest did you earn over those 4 years? Well, if I subtract the initial investment of $7,000, $1,805.36. Not bad for doing nothing. Now, of course, if this was $7 million that you put in a bank, every 4 years you'd be getting back an extra, million, which is pretty good. I mean, you could live off that. Just put a whole bunch of money in the bank and then come back every year and take out the interest and live off that and leave the initial investment in the bank. Actually, that's there's a word for that. I'm sure you've heard of it before, somebody called like a trust fund baby. Let me show you how trust fund babies work. Suppose I have a grandfather who was very smart with his money, and he created a chain of hotels, made a lot of money, and he wants me, his grandchild, to live comfortably for the rest of my life. But he doesn't want to just give me a bunch of money. So what dear old granddad is going to do is he's going to invest $1 million in a bank. And $1 million is pretty good. The bank's going to give me a good rate on this. So the bank is going to give me 7.75% interest compounded quarterly. All right, so Granddad puts this money in the bank. Now, I'm not allowed to touch this $1 million. I can't touch that. But at the end of the year, I can take all of the interest. So how much is this investment worth? At the end of the year. All right, Granddad, let's see. So I've got amount is the principal times 1 plus the rate over the number of compoundings to the power of the number of compoundings times the number of years. The principal is $1 million. 1 plus the rate is 0.0775. The number of compoundings per year. Quarterly. Quarterly means 4 compoundings per year to the power of 4 times at the end of 1 year. All right, so here we go. So let's find out how much this is worth at the end of the year. 1 million times 1 plus 0.0775 divided by 4 to the power of 4 times 1. This is worth $1,079,781, round to the nearest penny, and 56 cents. So the $1 million was the initial investment. That's how much Granddad put in there. At the end of the year, it's now worth that. So at the end of the year, I come along and I'm going to take out the interest, the $79,781.56. That's mine. But I leave the $1 million in there. So guess what? At the end of next year, there's another $79,000 waiting for me. If I can live comfortably off of $79,000 per year, I never have to work. Just every year I come back and just scoop off the interest and leave the original $1 million. And of course, this is how things work. Trust fund babies. Conrad Hilton did this for his grandkids. Not just $1 million, he put it in a couple of different banks. A Swiss bank, an American bank, a German bank. And then these the grandchildren just kind of go around from bank to bank every year and scoop off the top. They're not allowed to touch the initial investment. That money's put away in trust. They can't touch it, but they just go around, go to Germany this year, live for a couple of months off that interest, go to, let's see, where's the next bank? In the U.S., okay, we're going to go to the U.S., live for a couple of months off the interest, and so forth. Kind of an interesting way of living. All right, so now that's compound interest. There's another interest, type of interest. We've had simple interest, compound interest. Now we're going to talk about something called continuous. Continuous. I have no idea how to spell continuous. Where is it? U-O-U-S. So there should be a U in there. There should be a U in there. U-O-U-S. Continuous compounding. Now, in continuous compounding, obviously, the more we compound the interest, the more it's going to be worth after time. If you compound it just once a year versus something like twice a year, or quarterly, monthly, weekly, what about daily? Gosh, that interest would accrue 365 times. Yes, it would be a smaller interest, but I would be getting interest on interest on interest 365. What about hourly or every minute? Well, continuous is the most is an ongoing continuous interest, and we have a special formula for compounded continuously. And here, amount equals the principal. That's the same thing, times E. Yes, that's our E. That's the E that we always see. That's a constant to the power of the rate times the time. So we've got A is still the amount. The thing's going to be worth after time. P is still the principal. That's the initial amount that's being invested. R is the interest rate. And again, we have to put it in as a decimal. T is time. So all of these variables we know. E is not a variable. E is that number on our calculator, the number that we were using, the 2.78128, whatever it is. It's a constant. Just like pi is a constant we use with circles, E is a constant we use with compounding. All right, so let's take a look at an example. Suppose I go to the bank and I'm going to invest $8,000 at 6.125% interest, compounded continuously. UOUSLYCONTILU. That looks weird, but oh, that's right. I got it right. Ooh, okay. And I want to know how much would the investment be worth after 6 years. All right, so we've got our compounded continuously. The amount it's going to be worth is principal times e to the RT. Again, always write the formulas down, ladies and gentlemen, and then substitute the numbers in. The principal is at $8,000. E, the rate as a decimal point 0.06125 times 6 years. You know, that's a little confusing. I'm going to put them in parentheses here. And I would want to put this whole thing in the parentheses. We're about to see that on the calculator. So now on the calculator, put in 8,000, 3,000 times E. Now remember where E is, shift ln, e to the power of. Now if your calculator does E and then the little chevron, make sure you put that whole thing in parentheses. Open parentheses, 0.06125 times 6, close parentheses, equals, and it's going to be worth $11,552.90, round to the nearest penny, 96 cents. After 6 years. So if I subtract the initial amount, that's an extra $3,552.96. All right, when working with these formulas, I want to take a closer look at these, the two new formulas that we just talked about, the compounding formula and the continuous formula. Here's the compounding formula. How many variables are there here? Well, let's see. I've got amount, principal, the rate, the number of compoundings, and time. I've got 5 variables here. I should be able to give you any 4 of these and work backwards to find the other one. Just like with the interest formula. Here's the continuous. How many variables are there here? I've got the amount, the principal, the rate, and the time. There's only 4 variables here. Remember, E is not a variable, it's a constant. I should be able to give you any 3 of those and find the other one. Let's look at an example of that. Suppose in this next example, I'm going to invest some money, but I want to get a very specific amount. So I'm going to invest $8,200. I go to the bank. I've got $8,200. I'm going to put it away. I've been saving to buy a house. And I'm going to invest that, and I need $12,000 for a down payment on a house. I'm close, but I'm going to go to the bank, invest it in a CD or something, and this is my goal. Well, the bank tells me it's going to pay 8.875% interest, compounded. Let's see, we've done monthly, quarterly. Let's do monthly. We did weekly. I don't know if we did monthly yet. The big question becomes, how long? If I just put that $8,200 in the bank and walk away, They're going to give me 8.875% interest compounded monthly. How long is it going to take before I've got that $12,000? How long? And of course, this is, I'm not doing any other saving, I'm not doing anything else here. I just put the money in the bank, walked away. How long before I get that, reach my goal? Well, this is a compounding formula, not compounding continuously. So if I write the formula down, the amount is going to be the principal times 1 plus the rate over the number of compoundings to the power of the number of compoundings times time. Now, as I substitute in, I know the amount, $8,200. 1 plus, I know the rate, it's 0.08875 over, I know the number of compoundings, 12, to the power of 12 times, I don't know the time. I don't know how many years. The t is my variable. I don't know that. All right, so I want to solve for the t. Oh, and I know the amount. I want it to be 12,000. So how long does it take $8,200 invested at 8.875% compounded monthly to reach $12,000? So there's the story. I read you the story in English. There it is in math. This is what I want to solve. All right, here we go. So here comes the work to solve this. $12,000 equals $8,200 times. This is just some number in here. I can do 1 plus 0.08875 divided by 12 equals, and this is 1.0073958-ish to the power of 12t. I can't multiply these two together. Now take a closer look at this equation. It looks very confusing, but do you see, let me see, where I need a, do you see, no, not orange, where's my yellow? There's the yellow. Okay. So I want you to take a closer look at this and notice this should look a little bit familiar. It's almost like I've got a y equals a times b to the x. Oh, that didn't show up very well, did it? Well, this equals this times that to the power here. This is an exponential equation. Oh gosh, that didn't show up very well at all. But the idea is I've got something equals something times something to the power. This is an exponential equation. I'm going to solve this. I'm going to do it algebraically. All right, here we go. So the first thing I'm going to do is I'm going to divide both sides by 8,200. I'm going to get rid of that 8,200 by dividing both sides by 8,200. All right, so let's see. 12,000 divided by 8,200 equals 1.463414-ish equals 1.0073958 to the power of 12t. I know these, the numbers, the decimals are getting kind of awkward, but we're actually going to use our calculators to do a lot of these calculations. I want to solve for t. The problem is t is in the exponent. I need to get it out of the exponent. Well, how am I going to do that? I am going to rewrite. This is an exponential equation here. I'm going to rewrite it in logarithmic form. In other words, I'm going to, or maybe another way of thinking about it is I'm going to take the natural log of each side. When I take the natural log of each side, I'm going to have the natural log of that 1.463414 equals the natural log of 1.0073958 to the power of 12t. Well, what does this do for me? Well, now that I've got a logarithmic equation, I can use my properties of logarithms. The best property of logarithm is that I can take this exponent and put it in front. Again, the yellow's not showing up that really though, is it? Well, the t, and I'm going to leave the 12 there. I don't care about the 12, but the t exponent. So now I'm going to have the natural log of 1.463414. By the way, this is just some number. the natural log of this is just some number. I can do that on my calculator. Equals t times the natural log of 1.007395 to the 12th power. I leave the 12 there. This is also some number. That's just some number. If I do the calculations, these numbers are not going to be very nice numbers. Certainly nothing I could do without a calculator here. Let's see. What is the natural log of 1.463414-ish? There it is. So it's 0.3807772 equals t times, well, what's this? I'm going to do this on my calculator. The natural log of 1.007395 to the power of 12. And I get t times 0.088423-ish. Divide both sides by that. So I'm going to take my 0.380772 divided by 0.088423 equals, and I get 4.3. And we're done. We solved it. Remember, t is time in years. So the original question, I'm investing $8,200 and I want $12,000. How long will it take? Substituting into the formula, we knew everything except for time, and time was in the exponent. This is where we needed all of our rules of exponents, and dealing with logarithms, the final answer is going to be, it's going to take 4.3 years. No, that's not that long. Keep working, keep investing, put some more money aside so when you get into that house you can do repairs and upgrades and make it your own. So 4.3 years later, put that money in the bank, walk away, keep working. 4.3 years later, come back, get that money out, and buy that house. Of course, lots of things can go wrong in that situation. The house could have cost more, and you might need more money, or the houses might cost less. You might be able to buy a better house than you could have thought of. All right, there's one more thing that I want to look at when it comes to investing. And I want to look at something called the effective rate of the interest. The effective rate of the interest is a law, the Truth in Lending Act from many years ago. What happened was that banks would start doing different types of compoundings and different interests. And they would offer different interest rates with different compounding schedules, and it was very confusing. And it was very difficult to see, well, which one has the best rate? Which one has the best rate? We have two little formulas for this. For the compounding, we have that the effective rate, R sub E, R is for the rate, sub E means the effective rate, is given by 1 plus the rate over the number of compoundings to the power of the number of compoundings minus 1. If it's continuous, it's a different formula. Continuous. The effective rate of continuous, the rate effective, is E to the rate that they're giving you minus 1. All right, so what's going on here? Well, we're going to look at an example problem in a moment where you've got some money that you want to invest, and you go around and you want to get the most money back you can. So we're going to go to 3 different places, and each one of them is going to give us a whole different investment strategy. And how do we tell which is the best? Well, we can find the effective rate. The effective rate is also known as the APR. Does that sound familiar? That's the annual percent rate, or APY, which stands for the annual percent yield. These are the same kind of thing, the effective rate. And I'm sure that you've seen these in commercials, and if you've bought a house and a car, you've heard about, or if you've got credit cards, you've heard about what's the APR, the APY. If my credit card is charging me 11% compounded every monthly when I pay the bill, what is that the same as a yearly rate? Because maybe another credit card wants to charge me a different rate compounded quarterly or weekly or bi-weekly. I get paid every other week. Maybe I'm going to make payments every other week. And the investing can become very confusing. This levels the playing field so we can find the effective rate of any sort of weird type of investments. All right, let's take a look at an example. So in this example, we're going to have a fixed amount of money. We're going to invest, and the amount of money doesn't really matter. We want to invest, let's say, $6,000. And I want to know where am I going to get the most out of my money as I invest this. So I'm going to go around and I'm going to go to 3 different places. Now, ladies and gentlemen, I'm going to try to do all 3 of these kind of on the same sheet of paper here. So the first place is a bank. And the bank tells me that they'll give me a pretty good, they're going to give me 2.15% interest compounded monthly. All right, okay. The second place I go is a credit union. Now, the credit union says that they'll give me a better rate than that. They're going to give me 2.2%, but it's only going to be compounded quarterly. Oh gosh, straight away we can see the issues here. 2.5% is a lower rate, but monthly the compounding will take place 12 times a year. 2.2% is a better rate, but quarterly means it's only going to be 4 times a year. Which is the better investment? Well, after this I go to a day trader that will invest my money, and the day trader tells me that they will give me 2.12% compounded continuously. So all of these are completely different strategies. Which one is the best investor? Which one am I going to get most money out of? Well, in order to answer this, we have to calculate the effective rate. So the effective rate of the bank, is going to be 1 plus the rate 0.0215 divided by the number of compoundings 12 to the power of 12 minus 1. Oh, I wish I'd spread that. I wish I could have spread this out a little bit more here. All right, what's the effective rate at the bank? So I write the formula. Oh, you know what? I should have written the formula down first and then substituted it in. I was kind of looking at my notes here, and I just directly substituted it in. So my effective rate is going to be, open parentheses, 1 plus the rate that they're going to give me, 0.0215, divided by the number of compoundings, 12, to the power of the number of compoundings, 12. Whoops. That should be to the power of 12 minus 1. Oh gosh, have I got this right? Open parentheses, 1 plus 0.0215 divided by 12 to the power of 12 minus 1. Hit enter. My effective rate here is 0.0217, or in other words, 2.17%. That's my effective rate. In the credit union, this is also compounded quarterly, so the formula, the effective rate is going to be 1 plus the rate over the number of compoundings to the power of the number of compoundings per 1. So the effective rate at the credit union is going to be 1 minus 0.022, quarterly is 4 to the power of 4 minus 1. The credit union is really paying me 1, well, that should be a plus. How did that become a minus all of a sudden? 1 plus 0.022 divided by 4 to the power of 4 minus 1, and I get the effective rate is 0.02218. In other words, 2.218%. Oh, the credit union is a little bit better, isn't it? The credit union's effective rate is a little bit better. What about that day trader? All right, so for continuous, the effective rate is going to be e to the r minus 1. So the day trader, e to the 0.0212 minus 1. So shift e to the 0.0212 minus 1, and I get the effective rate is 0.0214, which is 2.14%. Now I can see the effective rate of each of, and I can compare these effective rates. This would be the annual percentage yield, or the annual percentage rate. 2.17, 2.21, 2.14. It looks like the credit union has got the best investment. That's the one that I would go with. All right, let's do one more. And on the next one, I want you to kind of pause the video after I set it up and set the problem up, and then see if you can do this. The problems 41 and 49 in the homework are ones where a little bit more interesting here, setting goals. So let's suppose we're going to invest. Let's say we've got a business now, a company. And a company is going to put some money aside. Let's say it's a golf course. And we're going to put some money aside until we reach a specific goal. And as soon as we reach that goal, we can expand our golf course. We bought the property next door, and we want to add an extra 9 holes, but it's going to cost us a lot of money. So we're going to put aside $150,000. We're going to invest it at 7.15% compounded weekly, and what I want to know is how long will it take to double. Suppose this golf course that we own, in order to create another 9 holes, it's going to cost me $300,000. Well, I've got half of that right now. I'm going to put it aside. This is a long-term goal. We're going to put $150,000 aside in a bank. How long before I can afford, how long will it take that money to double before we can expand the golf course? All right, so this is a compounding weekly. That tells me what formula I'm going to use. Amount is principal times 1 plus rate over n to the nt. Substituting in the principal, it's 150,000 times 1 plus my rate is 0.0715 over weekly is 52 to the power of 52 times t, and I want to know how long will it take $150,000 at an interest rate of 7.15% compounded weekly to reach 300,000. Double. This is very similar to the problem we just did algebraically. So go ahead and pause the video and see if you can figure this out. How many years is it going to take? All right, I'm going to go ahead and solve this here. Now, we would divide by 150,000 and we would get 2, and then take the natural log and bring the t out and divide. We can do that all algebraically. It's exactly like the one we just did, except the numbers are different. However, this one, I want to do it a little bit different. In this one, I'm going to solve it graphically. Now, graphically, if I graph my investment, here I'm going to have time in years. Here is, let's see, 100, 200, 300,000. So here's my initial investment of $150,000. And the money's going to grow ever so slowly. So there's my money growing. It starts at $150,000 at time equals 0. and the investment is growing and growing and growing and growing. Here is the 300,000 that I want. Where the investment grows and reaches the 300,000, that tells me how many years it's going to take. So I'm going to solve this one graphically. We certainly can do it algebraically. It would be exactly the same as the previous one, just the numbers would be different. So let's see, I got a bunch of junk in there. And my y equals. In y1, I'm going to put the $300,000 that I want. In y2, I'm going to put this. 150,000 times 1 plus 0.0715 divided by 52 to the power of 52 times my variable. I'm going to use x here. X represents the number of years. So there's my investment, and here's where I want it to be. Now my window, as I go to graph this, what would be the window be? Well, x is the number of years. I'm going to start at 0 years and move on. So my minimum, I'm going to make that 0. How many years is it going to take me? I don't know. I'm going to put in 30 years and scale in 5-year increments. It might be less than 30 years, might be longer than 30 years for this business, who knows. The y is the amount of money. Well, I'm not going to have negative. I'm going to start with 0, and I know I want to go to at least 300,000, so I'm going to go all the way to 500,000, scaled in 100,000 increments. So my x's, I scaled it from 0 to 30 years in 5-year increments. My y, 0 to 500,000, scaled in 100,000 increments, and I'm going to graph it. There's the line that I want. Here's the money growing. The intersection, that's when my investment is going to reach that goal. Now I can use the calculator to solve this by calculating the intersection point. So Casio users, you're going to hit G solve intersect. TI users, we're going to go to second trace, which is the calculate button. Calculate the intersect. Pick the two different curves. I'm going to pull the little cursor, and I'm going to drop a pin on this side, on this side of the intersection point. Hit it again, boom, there it is. And it tells me that the x value here is 9.7. The y value is 300,000. In other words, 9.7 years later, we've hit that goal of $300,000. And we can break ground on the new back 9. This is just another way. And we could solve all of them graphically too. All of them graphically or algebraically, either way. All right, ladies and gentlemen, so that's the end of the first application here, the financial application. What I'd like you to do now is I want you to go ahead and do the homework from 6.7. The homework from 6.7 is on page 481. And I want you to do problems 7 through 27, the odd numbered problems. There's a whole bunch of different things in there. Just substituting, write a formula down, substitute the numbers in, solving for different values, going back and forth. Two things to be careful. First, make sure you write the formula down first and then substitute the numbers in. And then it's all about the calculator, making sure that you're doing things in the calculator. Look at the answers in the back of the book. If you didn't get the answer, I would suspect that most of the time, if you don't get the answer, it's how you put something in the calculator. I want you to do 4 other problems, 31, 33, 41, and 49, which are more application problems. As soon as you're done with the assignment, I want you to email the completed assignment to me. And then I will enter the grades, and in this the new online version of this class, your grades are really based on the work that you're doing now, all of these assignments. And ladies and gentlemen, please don't copy the answers out of the back of the book. The answers are back there. But I want to see the formulas and the numbers substituted in, and then really a lot of times there's no much work after that. Once you write the formula down, substitute numbers in, a lot of it, except for the last couple we did, are just, everything after that is on the calculator. If there's ones that you're not getting, as I said, most of the time it's going to be probably because of how you're entering it in the calculator, so be very careful with that. All right, guys, well, good luck, and I will talk to you again. The last two sections are much smaller assignments, and they're just some very specific applications of using exponentials and logarithms. All right, guys, good luck. Talk to you again soon.